Hi, I'm MYDIN. I want to present based on question 1 from our assignment. So question 1 is type in this code and run. So this is the result after I run. Question B is we identify the lack of the signal since n equal to 0, 16 that give us 61 sample including both endpoint. Question C, we check if the signal is periodic with the frequency is omega 0.3 pi. When we divide omega by 2 pi, we get 3/20, which is a rational number. This confirms the signal is periodic. The fundamental period is the denominator, which is the 20 sample. Question D, we create the second signal x to n with the given parameter, frequency 0.22 pi, amplitude 3.5, and phase negative.
Assalamualaikum, my name is FATIMAH, S72359. I'm assigned of solving question number 2. This MATLAB code generate and analyze a damn complex sinusoidal signal. It starts by defining a time variable, decay rate alpha, and angular frequency omega. The signal st is a complex exponential that decay over time. The first plot shows the real and imaginary part of the signal over time. The second part displays the magnitude and phase, which are computed using f and angle function. This could help visualize how complex signals behave in both the time and frequency domains, which is useful in signal processing and communication system. In the first code, the signal starts from negative time, so we see oscillation before and after time 0. The damping is stronger due to a higher decay rate, so the signal fades faster. In contrast, the second code begins at the time 0 with a lower decay rate and higher frequency. As a result, the oscillation lasts longer and occurs more rapidly. The second signal also has a higher amplitude, making the plots more pronounced. Overall, the second output shows a longer lasting, faster oscillating signal compared to the first.
Hi, my name is JALIL. My number matric is S72070. In this video, I will explain question 3, which is about how the order of system affects signal when we use convolution in Matlab. First, we define plot and plot the input signal Xn and system H2n and H2n. Then we pass the input through H1n first, followed by H2n and plot the result. Next, we reverse the order, first to n, then H1n, and plot again. Although the intermediate result change, the final output yn remain the same. This show convolution is commutative linear time invariant system. Now we move on to question 4, which is involve convolution of two continuous time signal. The input is a triangular cross pulse and the system responds in an exponentially decreasing sine wave. We use MATLAB's convert function to compute the convolution and plot the output. The result is a most small and scratched out output. This shows how convolution spread and shape signal in time. Now for question 5, which involves applying a loss pass filter to different signal. First, we plot the filter impulse response. Now for question 5, which involves applying a loss pass filter to different signal. First, we plot the filter impulse response. Now for question 5, which involves applying a loss pass filter to different signal. First, we plot the filter impulse response. Now for question 5, which involves applying a loss pass.
In this analysis, we examine a transfer function using MATLAB. The script starts by defining the system zeros, poles, and gain, then converts the function into different form to extract meaningful data. It checks the system stability and uses the residue function to perform a partial fraction expansion. The output provides the residue and corresponding poles 5/3 at s equal to -4, 2/3 at s -1, and 2/3 at s equal to 2. Using inverse Laplace transforms, we derive the system impulse response as function equal to 5/3 exponential -4t plus with 2 over 3 exponential negative t plus 2 over 3 exponential 2t. Since there's a pole at s equals to 2, the system is unstable. This process highlights how MATLAB helps visualize and analyze dynamic system using poles, zeros and partial fraction. In this task, we analyze the system with the transfer function using MATLAB. By using MATLAB, we first define the numerator and denominator, then create the transfer function model using TF. We convert it to zero-pole game from with ZPK to extract the poles and zeros of the system. Next, we generate a pole zero map using PZ map to visualize system dynamics. To check stability, we use the isstable function, which returns whether all poles lie in the left half plane. Then using the residue function, we perform partial fraction expansion to prepare for finding the inverse Laplace transform. This helps us calculate the impulse response, HT. The process reveals the system structure and whether it behaves in a stable manner over time.